Hi, welcome back to Math 125. This is week 4. We're going to talk about linear correlation this week. We'll cover chapters 8 and 9 in our textbook. And again, please look over these measurable outcomes. Okay, let's review the coordinate system. So the Cartesian coordinate system, also known as the rectangular coordinate system, is basically based on two set of axes: the x-axis, which is horizontal, and then the y-axis, which is the vertical axis. And these two axes will divide up the entire plane into 4 quadrants. The first quadrant is on top right, second quadrant is top left, here's the bottom third quadrant, and then here's the fourth quadrant. So we go counterclockwise. And so this two-dimensional plane is known as the Cartesian coordinate system. And if we have any point on this plane is defined by an order pair, x comma y, where x is the distance as measured by the x-axis from the origin, and the y is determined by the vertical distance from the origin. The origin is actually this point right here, the middle point, 0, 0. And so, for example, if I want to plot 3, -1, then 3 is on the horizontal distance from the origin. Because it's positive, I go right, 1, 2, 3. -1 is the vertical distance on the y-axis. Because it's negative, I go down. So here's the point 3, -1. Here's some more example. -2, 4. -2 is the negative at x distance, so you go left. 4 is positive, so you go up. So that's -2, 4. And then 3, 3. 3 is positive, go right 3, go up 3. And then finally 0, -3. 0 is x, so that means we're at the origin. And then y is -3, so go down -3. So here's 0, -3. Okay, so now we want to look at data that compare two different variables. And so, for example, as a study from the statistician Pearson, he looked at the heights of fathers and their sons. And so there's a data set of about 1,000 pairs of heights. And so we want to plot this graph. And when we plot this, one way to plot it is to use something called a scatter diagram, which is a plot of the heights of the son versus the height of the father. And so it uses, notice these data sets, unlike the previous lectures, are now 2 variables. And so each dot is going to represent one father-son pair of their heights. And so, for example, if I pick a dot on this graph, if I look at the that point x comma y, the x coordinates tells you the father's height, and the y coordinates tell you the son's height. So this is every dot is a father-son pair that tell you their respective heights. And then, so based on this, right? I mean, this looks like there's some kind of a correlation between the two variables, meaning that as the height of the father increases, we see that there's a general increase in the height of the son, right? So all these points here, the height of the father is short, so the height of the son is also short. But points over here indicate that when the height of the father is when the father is tall, so is the son. And then another thing to point out about this graph is that if I look at this vertical strip here, it says that, so if you look down this vertical strip, this is 72 inches, which means that all the points in this vertical strip represent all the father-son pairs where the father's height is 72, right? All these points right here, or approximately 72. And so we see that we look at only the father whose height is 72, right? Notice the sons have varying height. Some of the sons are shorter, some of the sons are much taller, and so there's some spread, right, in the vertical direction, even if we fix the height of the father. And so that's something we want to look at later. Okay, so if there's a strong association between two variables, then if I know one variable, then it helps predict the other. But if there's a weak association, then that means that knowing one information doesn't help you predict the other one. And so in this case, we saw that there's a lot more spread around this line. This is the line that goes to the graph. That's a 45 degrees line. So there's some spread, right? Data is kind of spread around that line. And so that means that because there's a big spread, that shows there's some weakness in the relationship between the father's height and the son's height. Even though there's a general, correlation that trends upward, because there's so much spread, as we see in this photo strip, right? It's still a weak association, because even when we fix the father's height, there's still different degrees of height for the son. But here's an example where maybe there's a stronger association. So for example, if my scatter graph looks like this, or scatter diagram looks like this, then we see that all the points that kind of follow this line, right? It kind of follow. There's not a lot of spread between it's not too far away from the line. So this is a stronger association. Okay, so the idea here is that usually when we have a scatter diagram, we have this football-shaped cloud of points, a bunch of points. So here's some things that we can help summarize this scatter diagram. We can look at the average of all the x value and the average of all the y value. For example, the average of the height of the fathers, the average of the height of the sons, and then that gives us 1 point. This is called the point of averages. The point of averages means that that point, right, the x-coordinate is the average of all the x's, and the y-coordinate is the average of all the y values. We can also look at spread. We can divide spread into two directions, the horizontal and the vertical direction. So for example, if I look at this football shape and I just project all the points onto the x-axis, so look at only the x direction, then all these points here, notice there's a spread, right? And then we can look at 1 SD away. If this is the average, we can look at 1 or 2 SD away from the average. So this is the spread in the horizontal direction. We can also project all the points along the y-axis and see that there's also a spread there as well. And so we can look at all these points and only measure the spread in the y direction. So we can divide the spread into two different directions. So the summary statistics that we want to look at is the average of all the x value and the SD of all the x value. Again, ignoring the y value, look at only the x value, find the average, find the SD, and do the same thing for the y value. Ignore all the x value and do the same thing by finding the average and the SD of the y values. And so these will help us kind of understand more about our data. Now, but the thing is, we still want to measure the strength of the association between the two variables, because so far all those numbers tell us only in one direction. So the correlation coefficient, which we will define in a moment, is going to give us a measure of how strong the association is going to be. For example, the correlation near 1 means that the data points have a tight clustering. That means that if you draw a line through it, there's a line that it tends to follow. Whereas the correlation that close to 0 means that the clustering is looser and there's more spread, and so the correlation coefficient is the measure of the linear association or clustering around a line. The relationship between two variables can be summarized by the following three things: the average of all the x value, the SD of the x value, the average of all the y values, and the SD of the y values, and finally this correlation coefficient R. So all these numbers can help us understand better that association. Okay, let's look at some example value. Let's look at some positive correlation coefficient. Correlation coefficient can be positive and negative. So notice here, this correlation coefficient is around 0. That means that there's really no general association here. It's kind of scatter evenly around this quadrant. And then the association gets a little bit stronger when you get to 0.4, right? Notice now the clustering is a little bit tighter. It's said to be a little bit of a trend here that goes up. Then as we get to 0.6, then you notice it's even a tighter clustering. So the data now, there's less spread. There's a line that goes here, and the data kind of follow that line, but it's not too far away from that line. And as we go up to 0.8, which is closer to 1, we see that the clustering is now even tighter. And definitely we see a trend that goes up like this, and it seems to follow this line right here. As we get to 0.9, you notice it's even tighter, and the data now very, very close to that line. And then we get to close to 1, which is 0.95. We see definitely a shape of a line here, and the data tend to follow that line. Correlation can be between -1 and +1. It can be anything and anything in between, but it can be outside of that range. Positive correlation means that the cloud kind of slopes up. That means that as one variable increases, so does the other one. A negative correlation means that the cloud slopes down. So that means as one variable increases, the other decreases. So for example, here's the negative correlation. So as you increase x, for example, y tends to decrease. And so let's see some example of negative correlation coefficient. So this is negative 0.3. So again, it's still close to 0, so it's not much of a correlation. When you get to negative 0.5, it's a stronger correlation. But again, this is sloping down now, as before it was sloping up. As you get closer to negative 1, right, there's now a tighter clustering around this line, which is sloping down. And that line is, the clustering is tighter as we go up to closer and closer to negative 1. So here's negative 0.95. Here's that slope down. So again, as we increase x, y decreases. So the correlation coefficient is negative. And so here's one where it's almost negative 1. And we see that definitely there's a very tight clustering around that line. Okay, so now that we kind of understand intuitively how the correlation coefficient, let's talk about how to compute it. So here's the process. We want to convert each of the variable into standard units. And again, this is basically the z-score that we talked about in the last lecture. And then we want to find the average of the products of those standard units. That will give us the correlation coefficient. So again, this is confusing, so we're going to walk through this. So again, the correlation coefficient is the average of the x value in standard unit times the y value in standard unit. So find all the standard units in x and y, multiply them, and then find the average. For example, how do I calculate the correlation coefficient of this data set? Again, it's just a set of data points, x comma y, and if we graph it, we see it's just like that cloud, football cloud of points. So we want to take all the x value and we want to convert it to standard units, just like from chapter 5. And so this is a little bit of work, but we're going to just go through it. So again, the idea here is we need to find the average of all the x value and the SD of all the x value. Ignoring the y value, we do only for x value. So if we do this, the average turned out to be 4, the SD turned out to be 2. Again, we talked about how to do the SD a couple of lectures ago. And then once we have that information, we can take all the x value and find. Now this is our chance to try to find the standard units for each of the x values. For example, when you look at L1, how do I convert into a z-score or a standard unit? We take 1 minus the average, 1 minus 4 divided by the SD. Remember, this formula was used in the last chapter, chapter 5, on the normal curve, when we convert things into z-score. So convert all these into z-score. So 3 minus 4 divided by 2, etc. We look at all these points, subtract the average, divide by the SD. And so these points right here tells us how far each of those points are away from the average in terms of the SD. For example, for the x value, the average is 4. So it says that this data point 1 is about 1.5 SD to the left of the average. And for example, and 5, as another example, is half of an SD to the right of the average because it's positive. So all these are now standard units or z-scores. And so that result, we can make a table, and these numbers would go in one column next to it, and I'll show that table in a second. Now we do the same thing for the y value, right? So same thing, right? Look at all the y values, find the average and the SD, convert all these into z-scores. So let me and then finally we want to find the average of the products of those two calculations. So here's the table again. The third column, again, when we do this computation, we always want to do a table. This column is the x in standard units. Convert all the x's into standard units. The next one is all the y in standard units. Convert all the y value in standard units into z-score. Again, subtracting the average divided by the SD. And finally, the last column is the product of the x and y in standard units. So negative 1.5 times negative 0.5 is positive 0.75. So you multiply straight across. And then lastly, we find the average of this last column, which is our correlation coefficient. So the average of the last column is adding all these numbers, divided by 5. There's 5 entries. And then that's the correlation coefficient. This is a positive correlation coefficient of 0.4. So this says that there's a correlation, but it's a weaker correlation, but it's a positive correlation. That means that as x goes up, y tends to go up as well. Okay, so here's the intuition for how it works. So this is the scatter diagram from table 1. Right? All these are the 4 points that we have from table 1, and then we convert it into standard units. So here's the plot of all those points in standard units. So in other words, we look at these as points on the xy plane. So instead of plotting this, we're going to plot x and y in standard units. Okay, now that we've done that, we notice now that we're gonna, the way that this works is that we have to look at how these numbers correspond to this graph right here. So what's this graph? Notice this point right here. This point is the point of averages, and we see that if a point is on that first quadrant of this new plane, then notice that that point has a positive. So let's go here. So again, we're looking at the x and y in standard units. If a point is on the top quadrant, that means that that point is to the right of the average on both the x and the y coordinate, and so when we compute the product, we get a positive product because again these numbers are positive. But if a point similarly, if a point is also in this quadrant, that means that it's to the left of the average, both in the x and the y direction. That means when we compute the standard units, those will be two negative numbers. When you multiply them, you get a positive number. So 2 negative, right, multiplied to be a positive. So that means that if a point is below here, when you multiply them, it also gives you a positive number. So if you have a bunch of positive numbers here, if you have more positive numbers in this than in the negative direction, then the correlation will be positive, which means that we have a sloping up correlation. But if a point is on this quadrant or this quadrant, the second or the fourth quadrant, notice that then that point will have a negative product because this point is above the average of the y. It has a negative. It has a positive standard unit, but because it's below the the origin of the x axis, because it's on the left side, it has a negative standard units in the x direction. So when you multiply them, you have a negative number. So same thing on this side. Again, it's on the right side, so it should have a positive x standard unit, and it's going to have a negative y standard unit. So when you multiply them, you get a negative number. And so that's the reason why that works. When we average them, if you have more positive products, then you're going to have positive correlation. If you have more negative, for example, this one, all the points tend to have more negative products at the end. So again, negative product meaning this last column, then we're going to have a negative correlation. The correlate coefficient is first of all, it's a number. It has no units. Even if we look at the height, which is in inches of the father and son, the correlate coefficient by itself is just a number. So it's not affected by the following operations. If I switch the two variables, for example, if I put the height of the son on the x coordinates, height of the father in the y coordinates instead, if I flip it, it shouldn't change the correlation coefficient, right? That shouldn't change that measure of correlation. And then something else is that if we add the same number to all the values of one variable, that also does not change the correlation coefficient. In the same way, if we multiply all the values of one variable by the same positive number, that will not change the correlation coefficient. So again, that correlation coefficient will not be changed by switching the variables, adding the same number to all the x value or the y values, multiply all the values of one variable by the same positive number. And so here's an example why this is important. Suppose I look at a temperature between New York and Boston in a certain month, and we want to see whether there's a correlation between them. And so now, what if someone else look at the same data set, but they look at the data set in terms of Celsius instead of Fahrenheit? So if I look at the data set in terms of Fahrenheit, and they look at the same data set, but their data set is in terms of Celsius, then it seems like then it makes sense that the correlation coefficient should not be changed, right? Because if there's a correlation coefficient, if the temperature between New York and Boston has a linear correlation, then that correlation should not be changed whether I look at the data set in Fahrenheit or in Celsius. And so this result is very important. The idea is that if I convert my data set from Fahrenheit to Celsius, I'm actually performing these operations. If In fact, here's the conversion. To convert between Fahrenheit to Celsius, I have to first subtract 32. Based on the first condition, based on the second condition, it says that if I subtract or add a number, that doesn't change my correlation coefficient. After I subtract 32, I multiply by this coefficient 5/9. So, and the third, this condition right here says that if I multiply by a positive number, that also does not change the correlation coefficient. So converting between Fahrenheit to Celsius involves subtracting a number and then multiply by another number, and neither of those operations affect the correlation coefficient. So this makes sense, right? And something else to be careful is that the correlation coefficient are measure linear association, but not association in general. For example, if you have here's a couple of things where the correlation coefficient can be misleading. One case is that when you have an outlier, for example, all the points seem to be perfectly on this line, right? So it seems to be an association. But if you have an outlier, something way over here, then that will skew and give you a misleading correlation coefficient. Same thing here. This seems to have an association, but it's not a linear association. Follow some kind of this maybe a parabola or something. So this is a non-linear association. There is an association between the two variables, but it's not a linear one. So the correlation coefficient, if you try to find the correlation coefficient here, it can be misleading. And so as in the first example, without outlier, the correlation coefficient is almost close to 1, but with the outlier, the correlation coefficient is 0. So that's why we shouldn't use correlation coefficient for all data sets. In this example, for example, the correlation coefficient is almost 0. It's actually, yeah, but we see that there is an association, but not a linear one. Okay, so here's some more example. So we have to be careful when we look at the actual data sets. For example, if you look at school children, it seems like the shoe size strongly correlated with reading skills. In other words, the bigger the shoe size, the better they read. And so we have to be careful that if we look at only those two variables and we find the correlation coefficient, we might be tempted to conclude that shoe size does correlate to reading skill. But we have to be careful. Even though there's that strong correlation, it doesn't mean that if you have bigger feet, that you're a better reader. Instead, that there's another factor here, age, that's actually involved, right? And because as children get older, they learn how to read better, right? And so, and obviously, as they get older, they have their feet size grow, and so we have to be careful that correlation measure association, but association is not the same as causation. In other words, in this example, right, big feet doesn't cause you to be a better reader. So we have to be careful that we don't falsely think that association is the same as causation. Here's another example. During the Great Depression, it seems like they have some data that indicate that better educated people tend to have shorter spells of unemployment. So does that mean that education protects you from unemployment? Well, maybe, but we have to be careful here as well. Is that it turns out that age was also a confounding variable in this case. Remember, you look at the first week reading assignment, we talked about confounding variable. So the younger people tend to be better educated. This is just tend to be true, and it actually still is true, as the young people tend to be better educated, and this education level has been going up for over time. Now, given a choice in hiring, employers tend to prefer younger job seekers, and so if we control for age, then suddenly the effect of education on unemployment seems to be weaker. So that's why we have to be careful that we don't. We need to take into account confounding variables that might affect our data set. In 1955, Sir Richard Dahl published this article that shows the relationship between cigarette smoking and lung cancer. One piece of evidence was that he used the scatter diagram to show the relationship between the rate of cigarette smoking per capita and the rate of death from lung cancer in 11 countries. And so the correlation between these 11 pairs of rates was 0.7, and so this was taken to show the strength of the relationship between smoking and cancer. However, we have to be careful here as well. It turns out that yes, sure, that this correlation coefficient is very high, but it's not. If you look at rates between country and try to find compare rates, then we might have misleading answer, because it's not the country that smoke that get cancer, but it's the people. So if you want to measure the strength of relationship between smoking and cancer, we have to look at people, not just the rates of a whole country. And so, but of course nowadays, we do have data that shows that smoking does indeed cause cancer. But the point here is that correlation that we look at based on rates or averages, say of a whole country, can be misleading. So here's another example. According to the current population survey of 2005, if you look at the correlation between income and education for men between 25 and 64, then the correlation coefficient is 0.42. So that there's correlation, positive correlation between income and education. Now, if I look at each individual state, however, let's say look at each state and then compute the average education level and the average income. So now we just take each state and find the average. So we kind of look at the average instead of all the people individually. And then we compute the correlation between the 51 pairs of averages. Again, 50 states plus the DC, Washington DC. So if we compute the correlation coefficient between the pairs of averages, the correlation coefficient goes up much higher. So this is what I mean is that we have to be careful that we don't look at the averages and then look at the correlation of the averages, because that can be misleading, as this example shows. And the reason is because if you look at each state, there's a lot of spread around the averages, but by replacing the whole state with one number, which is the average, we're kind of eliminating the spread, and we lose that information, and so our correlation coefficient can be misleading. So this is called ecological correlations, which when we look at correlation based on averages or rates rather than based on individual data points. So these are often used in political science and sociology, and they tend to overstate the strength of the association. So you have to be careful of that. So again, right here's the picture for it. You look at individual education and individual income. Here's all the people and the income and education. But if I put them into groups of states, say A, all the people in that is denoted by A is in the same state. Everyone in B is the same state. Everyone in C is the same state. If we replace all of A with 1A, which is the average, all of B with 1B, which is the average, and all of C, which is the average, notice that the correlation of the averages tend to be along a line, but the actual data set, there's a weaker association. There's more spread. But here, when you replace with the average, we don't see that spread anymore. So that's why looking at correlation coefficient of averages on the right, it can be misleading, whereas the actual data set seem to be indicated that the association is much weaker. Okay, thanks for watching. Please work on what worked this week.